supporting supporting these Odyssey tools at Stanford and hosting Atlas office hours. So looking forward to spending some time with you all today on Odyssey and Atlas. So maybe I'll just kind of go through the order that people are on my screen. Rosetta, would you like to introduce yourself?
Hi, everyone. I'm Rosetta. I just joined Priya's team. I am a biomedical informatics data scientist. This is my first time generating a cohort. I actually need to generate a new concept set. So I wanted to get your feedback on it and see what the proper, I guess, workflow is for generating it, so that I'm not creating extra things that I don't need to have there.
Cool. Randy?
There, my name is, can you hear me okay?
Yep.
Okay, my name is Randy Painter. I'm an epidemiologist with Population Health Sciences. I've just joined this team. I was previously at Stanford Healthcare. So with Stanford Healthcare, I was a research scientist. And so I attended the STAR like annual meeting. Yeah, the STAR meeting last year. I attended all of the sessions this year. Really excited to now start getting access into STAR and know a lot about like the patient data side, about what goes into it, and now excited about the actual like research side on kind of this side of it. And so, yeah.
Nice. Maybe Hang or Hong?
Yes, good morning, everyone. My name is Hang, and I'm working at the Asian Liver Center at the School of Medicine with surgery department. So I'm a research scientist. I've been working with a bit of clinical data and then Optum data, all the clean data. And I'm new to Atlas, so I just want to know what it is and what I can use for my job.
Okay. Pratt?
Hey, hi, I'm Prati. I work as a research data analyst for Child Neurology Department. I usually work for like most of the PIs. They request me different kinds of cohorts creating in STAR. And I recently came to know about Atlas and thought maybe Atlas would be much more like have more options and have like more features rather than working on STAR. So I thought maybe I can explore more using Atlas rather than using STAR.
Okay, great. Mia?
Hi, my name is Mia. I'm a clinical research coordinator at the Sean Parker Center on campus, and I am hoping to use these resources to recruit and find people who might be interested in my study.
Nice, okay. Are you saying like outside of Stanford or within Stanford?
Either or, whatever works.
All right, and then we'll go through our instructor team. So Hannah, maybe you can go next.
Sure. Hey everyone, I'm Hannah. I'm a data scientist here at Stanford. I started around 3 months ago, so I'm still kind of learning, but also kind of available to help. So yeah, I'm kind of joining this workshop both as someone to learn and someone to assist. So yeah, nice to meet everyone.
Azad?
Hi everyone. Nice to meet you all. My name is Behzad, and so I'm a postdoc at Stanford, 2 years at the my second year's postdoc, and so my major is computer science, and I'm working on predictive modeling using the Odyssey tools and conducting network studies to evaluate the generalizability and transportability of the machine learning models over the CDM databases. And today I will provide you with the Atlas specifications to conduct such reproducible research over the CDM databases. That's all.
And maybe Priya, I'm hoping everybody knows Priya, but Priya, if you want to introduce yourself. Does anyone not know Priya?
I think she's
Yes,
dealing with a plumber right now, so she might not be at her desk.
Okay. All right. Well, we'll Priya is sort of our leader and coordinator of this training, and yeah, so we'll jump into it. Does everyone have access to Atlas? So you should be able to go to odyssey-atlas.stanford.edu. I'll put this link in the chat. Maybe you can confirm that you have Atlas, that you're able to log in and see your username in the upper right-hand corner. Oh, thank you, Rosetta. You can give a thumbs up or just shout out that you are able to log in. Randy, thank you. And Prati, thank you. Mia, okay, good. And Hung, are you able to access it?
He just said yes to me. We were direct messaging, so I think it only went to me. Oh yeah.
So Hung, are you able to log into Atlas?
Yes, I do.
Okay, perfect. So everybody has access now. All right, I'm going to start with a little bit of background overview. It's good just to check that we all have access. I'm going to start with a little bit of background overview, not too much, but just some slides on what we're doing with Odyssey and the OMOP common data model. The data model rests on the vocabulary, a set of standardized vocabularies, and the data model has a set of tables. So this is kind of what the data model looks like. There's a person table that has one record per person, and kind of your demographic information. There's an observation period table, which just gives you the start and end dates that the person was under observation in the Stanford Health data. Then we have like a visit table and different domain tables like conditions, drugs, procedures, device, measurement, etc. The vocabulary and the data kind of are linked in a very strong way, in that not only are we putting the data into this format, but we're also standardizing the codes that we use to represent the data. So that means even if you have ICD codes in your original source data, they are going to get translated into SNOMED codes or into some standardized vocabulary when they're mapped into this format. The reason why we do this is so that each OMOP CDM uses the same set of codes to represent the data. And that way we can build standardized analytic tools that will run on all OMOP CDMs because they're all using the same code sets. So the vocabulary, in the vocabulary, we have concepts. These are just another term for codes. However, we think of it more like a concept is like a clinical idea, and there's a code that represents it. And we don't want to have duplication in our standard codes. So typically our goal is to have a set of standard codes that that represents all of the clinical kind of facts that you could have, but not have duplication in there. These concepts have relationships with each other. So there's a lot of different relationships in the OMOP vocabulary. And one of the most important ones is the hierarchy. So some codes have descendants to them, or concepts have descendants to them. And so we can represent those in the concept ancestor table. And this allows you to select one code and descendants, and you can include all the descendants. You can also exclude descendants of a particular concept. But this is a useful, it's a useful aspect of the OMOP vocabulary. This is kind of what the concept table looks like. It's just a huge table with every single code system that you could imagine in it. And it has SNOMED, ICD, CPT, etc. And so this is all of the possible codes you could have. There's a lot of different coding schemes out there. And so what we do is kind of just standardize it into one format. We have the vocabulary that it's from. We give it a new ID. So when we're talking about concept IDs, these are IDs that are specific to the OMOP vocabulary, and they're unique. They will uniquely identify a code in this vocabulary. They will never change, and they'll always be maintained and move forward. So this concept ID 313217 is always going to represent this SNOMED concept, atrial fibrillation. And the reason we have to do that is because sometimes there may be other code systems that have the same code. The concept code is the original code in the SNOMED vocabulary. So that's 494360004. And then we have the standard concept field, which if it's S, it means it's denoted as a standard concept.
Randy, did you have your hand up for a second there?
Yeah, I did. I had a couple of questions, I guess, already. So so going back a couple of slides, when Adam, when you were talking about just the concepts, so kind of concepts on the same level, and then kind of the hierarchy. Yeah, concept relationship, concept ancestor. So can you give just really like high level, just like what would be like for example, direct relationship, like a concept, an example of a direct relationship between a concept relationship and then multi-step hierarchy. Like I'm thinking here, maybe like I've seen that in a hierarchy. I mean, in a like Odyssey talk, right? But like concept relationship, I guess what would you be talking about there? And then the other question as you moved along, when you're talking about these different like codes for the concepts for those same things, is there one that is that's like the standard or the predominant one that you're talking about in Atlas, that's like the gold standard, or are all of these just, is it all just like very fluid when you're talking about like AF?
Yeah, okay, so we're gonna try to maybe like find the concepts for atrial fibrillation, right?
Yeah.
So
Adam, if you want, you can use the Athena because the Athena's interface is good to, Athena can show the hierarchy, and so would be great to understand, yes, the relationships and the hierarchy.
Okay, so here is a code for atrial fibrillation. This might have been the one that we were looking at. Let's see. 313217. So yes, this is the one here. So to answer, I think, your second question, these are the relationships. So here's like the name of the relationship: associated finding of atrial fibrillation excluded. Focus of, has module, has finding site. Different concepts will have different relationships. But the big ones that we use a lot are is A. That means it. These are the parents, the direct parents of this code: fibrillation, atrial arrhythmia, supraventricular tachycardia. The other relationship that we might care about a lot is subsumes. These are all the direct children of this concept. So AFib and flutter, AFib with rapid ventricular response, etc. There's another really important relationship, which is the codes that get mapped into this. So, for example, let's take this ICD-9 code. So here's an ICD-9 code for AFib that might exist in your data somewhere prior to the switch to ICD-10. And when we map it into the OMOP CDM, we're going to use this relationship, non-standard to standard map, which tells us how we're going to translate this ICD code into this SNOMED code. So it tells you that when we see this code in our source data, this is a valid code, but it's not standard. So we use this relationship here, non-standard to standard map, and map it to the SNOMED code. An example of how we might use this is, let's say I want to build a concept set for AFib. I would search for AFib, or this, maybe I copied the wrong thing. Oh, that's the concept.
Adam, can you also show the hierarchy, and maybe the hierarchy reveals, yes, this part is very interesting, and so everyone can understand the hierarchy we have in the concept IDs.
And is this the standard, is the standard like IDs for Atlas and Odyssey, is it SNOMED?
For conditions,
it's being used?
yes, but not for
Okay.
procedures or measurements or other things. So yeah, for conditions, generally, not to say 100%, but mostly it's SNOMED.
Okay. Thanks.
And for drugs, it's RX norm, and an extension to RX norm. And for procedures, it's a little bit all over the place, but oftentimes CPT and HCPCS. But yeah, this gives you the like a graph depiction. Here's our atrial fibrillation concept. Here are the children, and here are the parents. And you can see there's a whole hierarchy here. And this all comes directly from SNOMED. So Odyssey didn't create this. What Odyssey does create is the mappings from ICD-9 to SNOMED. As well as sometimes there are vocabularies that Odyssey does create, but generally they try to just inherit existing vocabularies. Okay, so what we
Sorry,
want to
quick
do.
question.
Yep.
So in the concept for atrial fibrillation and flutter, that's a, I guess, child concept of atrial fibrillation. So will something that's a combination of two concepts always be a child concept for both of these? Does that make sense?
Yeah. That's kind of a SNOMED question, and I don't know for sure if that's the case or not.
Okay.
Yeah, I don't know for sure.
Just curious. Okay.
Bizad, do you know if I guess
Mm.
it has to do with how SNOMED is constructed.
I'm not sure. Yeah.
Okay. Good question though. And as you have questions, just feel free to shout them out. I can't see the hands when I'm sharing my screen, so just unmute yourself and shout the question out. And also, if you want to see something in particular, the training is for you also. Let me know if you want to explore some particular thing in more detail. What I wanted to show is constructing a concept set and using this kind of hierarchy to do it. So here we have a concept ID 313217. So this is the SNOMED code. For some, it's a little strange that I didn't see that there. We can import directly a concept, say add to concept set. So here's an AFib concept set, and here we have one concept. And we'll save it. We'll look at included concepts. So we have a record count. So this is how many times does this code occur in our database? And then DRC is descendant record count. So how many times does this code or any of its descendants occur in the database? So what I can do is click descendants here. And if I save it, then, so if we look at included concepts, now there's 16 concepts that will be included. And these are all these descendants. So permanent AFib, exacerbation of AFib, rapid AFib, etc. So you can see those concepts here. And some of them are contributing a large number of records to our concept set. So it'll help us pick up more people.
So, excuse me, so RC is record count
Yep.
and DRC is, what does that stand for?
Descendant record count.
Okay.
So that means the number of records for this particular concept or any of its descendants.
So record, is that, does that correspond to the number of encounters or the number of patients?
Just number of kind of events. So I wouldn't use the term encounter because you may get the same record for the same person on the same day. And that may be kind of a bit of double counting. That can happen. But it's just how many times does this code occur in the database? I think
Okay.
oftentimes though, yeah, you might think of it as encounters, as like, yeah, number of times it occurs. But yeah, I hesitate to use the word encounter because it kind of has a connotation with like a visit, the idea of a visit.
Adam, can we say, for example, all these are the conditions, and so this is the number of records that we have in the condition occurrence table. Is that correct?
Yeah, that's correct. So we can see the domain of the domain tells us, which domain it is, and each domain has its own table in the database. So in the condition table, this is how many rows in the condition table, that this code appears.
And the other thing is that, for example, in some cases, you can see the record number and the DRC number is different. When we have a different number, it means, for example, in ID 42, we have 90,000, but in the about yes, for example, in this, as you can see, these are our own concept ID. For example, here, this is this concept ID includes can be considered as a parent, and so it has some children, for example, and so as a result, the DRC number is greater than the record number. However, in the record below that, we can see this, we have the same number. It means this is actually the leaf, and so we don't have any child, and this is the end of the hierarchy, and so we don't have any concepts under the given concept.
I have a quick question on that. So in the DRC, how many layers down does it go? So for atrial fibrillation, that's like at the top, and that like 1.4 million records, is that just all that's so everything that's listed here, or does that also include any of these concepts children?
This is in the concept ancestor table, and so in the concept ancestor table you can see the level of the hierarchy. For example, each can you go to the for example to the Athena
that DRC number just first level, so it doesn't then go in, doesn't then go another level and also include all of the child concepts of these 10 concepts?
Yeah, it does. It goes all the way
does?
down.
Okay, so if we went one up from atrial fibrillation, so say, I can't read that, but whatever that is, so we did that includes atrial fibrillation and then all of the children in the row counts.
Yes.
Is that right? Okay, cool. And then are those included in the concept set? The children of the children?
Yes.
Yes. Okay, so everything below is included.
Yep.
Okay, cool. Thanks.
Yeah, because we selected descendants here, it will include all descendants of this concept. So it looked to me like, okay, persistent atrial fibrillation has a child, I think. So if we click here, okay, so yeah, we can see here's AFib, here's persistent AFib, and then long-standing persistent AFib is another level down. And so you can see that's included here. So when we have the record count for persistent AFib is 90,000. And when we add to it, its only descendant is this 7,800 records for long-standing persistent AFib. We get 97,900 records for the descendant record count. And all that's included in this 1.4 million. So 1.4 million is all the record counts for all of the concepts in this concept set.
Great, thank you.
Okay, so I think we should go ahead and just jump into creating a cohort. And what I would like to do, if possible, if someone has a clinical question that they would like to explore during the training, I'd like to see if we can come up with something that might be interesting to the group. Could be something you're working you're working on now or an area that you are familiar with.
Adam, before going, can you show how we can exclude some IDs from our concept sets? And so it would be great to show. Yeah.
Oh yeah. Okay. So the export.
No, export now. How we exclude, for example.
Exclude. Yeah.
Exclude.
Okay. So let's say this is your concept set, and you want to exclude long-standing persistent AFib because you're interested really in like a new AFib. So all you do is click this and then click exclude, add to concept set. And now our concept set expression looks like this. It's AFib and all descendants. And we're excluding this one code. So if we look at included concepts, that concept is no longer there. Now, what if I wanted to exclude, say, persistent AFib and longstanding persistent AFib? Well, I could exclude that like this. So I've now added both of these here. But since longstanding persistent AFib is a descendant, I can just exclude the descendants, and I will remove that one. So now we're saying we want all the descendants of AFib to be included, but we want to exclude longstanding persistent AFib and any of its descendants. Oh, sorry, I think I've actually messed up a little bit. Let's go to persistent AFib, exclude its descendants, add that. And then we can remove this. And now we have a simpler concept set where we're excluding this persistent AFib. And if we look here, we should not see longstanding persistent AFib.
But if you don't hit the exclude descendants, it will include the descendants
Right.
of that, even though you're not including that particular one.
Right. Yeah, so let's say I exclude things individually. So here I'm excluding them kind of individually. I can click this optimize button. And what this will do is look for, oh, it says it's optimized. Okay. I don't think it's, well, what it will do is it will try to make a simpler concept set definition, which I would say like you could make this a little simpler by just clicking descendants here and removing this. And that will give you the same thing. So this is important when you want to build a code set that represents your clinical idea, and it might happen that you can use this descendancy relationship and the inclusion or exclusion to create kind of your curated set of concepts that you want. I wouldn't worry about mapped. What map does is includes the source concepts. So if we say mapped here, now we have a lot more included concepts, but these are non-standard. So this is everything that gets mapped into AFib has been now added. But since all the data is stored using the standard concepts, generally you don't need to do this, and so usually you don't have to worry about mapped. You can just leave it unchecked. You can export this and save it. There's a JSON format that you can use to save this concept set expression. So you can see we have the information about, is this excluded? We're including descendants. That's true. We're not including maps. You can also have the included concept identifier list. This is just a comma separated list of all of the concept IDs. If you want to import a concept set from someone else, you can do that here. So if I go to Atlas demo, I can show you how to import a concept set from someone else. So let's look at this Alzheimer's disease. We can go to export here, copy the JSON, paste it here, or go to concept set, paste it here. You can overwrite or append. So we'll just append. And now you can see we have added Alzheimer's disease here, which I'll get rid of, but I just showed you how you can import concept sets from like the public version of Atlas or just any other Atlas instance. So let's think about, brainstorm together a clinical question that we might be interested in. In particular, we're kind of going to aim towards doing some prediction work. So does anyone have an idea for a prediction analysis?
I have I guess, a patient subset that I'm interested in generating.
Okay.
So there's certain diagnoses that these patients have, and then I'm interested in getting their nutritional intervention and see if that predicts their stay in the hospital or like their prognosis.
Okay.
Do you want me to give you the diagnoses that we're interested in?
Yeah.
So it would be, I think the first one is, it's called Ehlers-Danlos syndrome. I don't know how to pronounce it. I think it's spelled EHLER -DANLOS. That's the one. Yeah. And there's no concept set for that one in Athena just yet. So I think we would have to, or there is one, but I don't think it pops up in Atlas.
Okay. Actually, so one thing that I like to do is look for, well, let's try it here and see if anything comes up.
Yeah, when I search it there, it comes up, but when I go under concept sets, it doesn't come up.
Right, no one's made it yet. Yeah. Okay, let's look at Atlas. Oh, this is Atlas demo. Okay. We can close that. Let's go to data sources. And this is going to be a condition. And we can just quickly look to see if there's conditions in our database. Table. Okay, so here it is. Does this seem about right for the prevalence? Like pretty low. Yeah.
Yep.
Okay. So let's create a concept set for this first. Oh, if we click on it, then we load a drill down report. So this is 79145. And you're looking, so what are the nutritional interventions that you're looking at?
So some of these patients can have total parenteral nutrition. Some of them can have intravenous fluids, which is the total, and then there's parenteral, and then EN, I forget what it stands for. Let me Yeah, enteral nutrition. I'm going to type these up in the chat.
Okay, perfect. All right, so we created a concept set. We can take a look at the record counts and descendant record counts. It's the first step. And then we're going to build a cohort definition. So a cohort is going to be a set of persons and a duration of time for each person. And a person can enter and exit a cohort multiple times, or they might just enter once and stay in it until they are no longer under observation. But there's 4 kind of boxes that we have to fill out to define our cohort. This is probably the most important functionality in Atlas, some of the most useful. And so this is really where I think you can get the most value from using Atlas, is in building cohorts and then using them in downstream analyses. So we have our concept set. We need an entry event. So what's the event that's going to cause a person to enter this cohort and start being in the cohort? Well, that's going to be this condition. So now we've imported that, and this will capture each person that has this. We can leave it there if we want and just stop there, and that's going to be a very simple cohort. If we want to add inclusion criteria, we can do that down here. We can restrict to earliest event or all events or latest event. We can decide when the person exits the cohort. So we have some options there, but this is a totally valid cohort. And it's pretty much the simplest one you can create. And then we can click generate, and this will show us how many patients we have in that meet this criteria. So a person will enter this on their first in their first instance of this condition. The Ehlers-Danlos syndrome, the ED syndrome, and they'll exit at the end of observation time.
Is it possible to add any exclusion criteria?
Yep. So what would be one you might want to add? Like age, maybe, or
maybe we can try to add people who underwent any kind of chemotherapies or any other conditions. They shouldn't be overlapping with this specific condition.
Yeah. So what would be an example of one that you want to add? Did you have anything in mind, Rosetta?
Not really, but I guess maybe age could be an interesting one. Yeah, because I imagine children may not be. Let's see.
So here we have age greater than or equal to 18 as an inclusion criteria.
Sure, this may not be physiologically relevant, but for the purposes of today, it work.
Okay. We can add multiple inclusion criteria, and it could be based on, so say you did want to exclude people who had a prior condition. We could say exactly, so say exclude prior X condition, whatever. So we would say they must have exactly 0 occurrences of whatever condition we want to put here. All days before and 0 days after the index start date. So that's how we would add an exclusion based on prior conditions. We can combine logic in very complex ways here. So suppose we wanted to say they must have all, they have to have no prior conditions, no prior measurements, no prior procedures. You can do this. You can add a group and kind of, combined and or logic like this. So this lets you do, say having at least one drug of a certain type, or a different drug. So either this drug or this drug within a certain time frame relative to index. Yeah, you can get fairly sophisticated with these cohort definitions. You can also add nesting criteria. So this will let you specify conditions like a drug and then, or like say two occurrences of a drug within 30 days of each other, something like that. Or at least 30 days apart, two occurrences of drug that are 30 days apart. Something like that. So
Add another inclusion criteria in there. Since I guess they're gonna have nutritional interventions, it might be I don't know how best to do it. Only restrict this subset to patients who have been admitted for GI related syndromes, or can we exclude those who have been admitted for anything else? Like, I don't know. I mean, in this case, since we have just one criteria, would be best to add additional restriction or additional inclusion criteria, right? And then
yeah, I'm not sure because I'm not I don't know enough about it, but are you saying that you might want to restrict people who you want to make sure that they're admitted to the hospital for this condition?
for GI related condition, because some of these patients will not. And since
Okay.
I'm interested in nutritional interventions, I wanted to subset these patients.
Okay, so in that case, I think the entry event might be a hospitalization event.
Mm-hmm.
Okay, let's do that. Let's structure it like we'll say a visit. That's going to be a visit, and inpatient visit. I'm assuming it would be inpatient.
Yes, I think so.
We'll delete that, and we want to make sure we're including all events. And then we are going to take the first one that meets all of these criteria. So they have to be age 18. They also need to have this condition. Now, this condition might show up within some time range relative to the inpatient event.
Can be anytime, I imagine.
Well, I mean, this is a particular time in a person's history where they're admitted for. Okay, so this one would be anytime, but we need a GI diagnosis, right? Because we're kind of trying to say that the visit is for a GI related
Yep.
issue. Okay, so let's make a concept set for this. Now let's look, I don't know, maybe
First
classification.
one, or irritation is fine.
Actually, I'm going to look in our data sources tab here again. And condition occurrence. So it looks like this might be the biggest one.
Mm-hmm.
Is that person count? Is that including descendants of this or just this concept?
It is including just this concept.
Okay.
Weird timeout. Okay, so let's just going to download this as a CSV, and I'm just going to take a bunch of these concepts. We'll make a new concept set. Import descendants. So here's our concept set, and we'll take out the non-standard one. Is there anything else in here that we should remove?
Maybe the tumor one. I think it's 3653. Concept. Yeah, that one. And then the one under. Sorry. Oh, there's like actually
There's a
multiple.
few tumors, yeah.
Okay. Let's search tumor. We'll get rid of these three. And I mean, here's a cancer.
There's an influenza one in there as well. I don't know if that one is.
That might need to be removed as well. Yeah.
Okay.
There's a complication of procedure as well. Does that mean like well, yeah, I guess a procedure complication.
Yeah, that would need to.
Which one are you looking at?
I just saw the word procedure in one of them. Hold on, where did it go? Yeah, there we go.
Okay.
Oh, and then the prosthetic device as well, maybe.
Okay. Let's try optimize and see if this makes it smaller. Okay, so we can remove a couple. We'll say overwrite. Imaging of gastrointestinal tract abnormal.
Maybe, yeah. Because that would indicate tumor potentially.
Okay.
Or I don't know, honestly.
Injury.
Yeah, I think that would need to be removed.
And
What
about that last one? Erroropathy.
Yeah, maybe.
Okay, well,
The injury could be related to the Ehlers-Danlos syndrome.
What's that?
The injury could be related to the Ehlers-Danlos syndrome, so I would keep it.
Okay, all right. Let's go back here. This one, injury of gastrointestinal tract without open wound. We can add that one back. But this is kind of the process that we go through to try to get these concept sets built. We'll stick with that for now, and then we'll say that they must have some sort of GI diagnosis. So we'll say condition occurrence, at least one. Import. It's gastrointestinal concept. And now we're going to use time. So should we say sort of like 1 day before and 1 day after, or 7 days after? We can also just
A
do,
question on index start date, if that's okay.
yeah.
So for this one, is each inpatient visit, so I assume the index start date is referring to when someone enters based on the cohort entry event. So in this case, it's an inpatient visit.
Yep.
So if say one patient probably has multiple inpatient visits, is each one of those an index start date, or is it the first one, or does it depend?
Yeah, so if I select, this is where I kind of choose that. So here, I'll say all events. Suppose I didn't have any inclusion criteria. I just had a visit occurrence of inpatient visit, select all events, and I selected all events here. And then I said they exited, say 1 day after that visit. Then they would essentially enter this cohort every time they had an inpatient visit, and then they would exit it the next day. And then the next time they came back to the hospital, they would re-enter the cohort.
Okay, so for this one in particular, I don't know really anything about this disease, but if it's like a lifelong condition that you have, would this configuration as it is now, where every time they're entered into the hospital with a GI issue, they enter the cohort, is that going to be a like repeated information, if that makes sense? Like, so is one patient going to be in the cohort, say 10 times, and could that like skew the results?
Yeah, I think the way that I would set this up is where I would look at every single inpatient visit as a potential candidate for an entry event. And then the first one that meets all the inclusion criteria, only use that one.
Okay.
So that way they would only be in once. But we're going to look at every single inpatient event that they have. And they have to have for the Ehlers-Danlos syndrome, I guess this is a question of would this be something that would be diagnosed before? I'm thinking we shouldn't look in general, like we want to be really careful about looking into the future, because there's just a lot of bias that can happen in your analysis when you do that in your definitions. I think it's okay if we say like, okay, they might have this like the day after, while they're in the hospital or something. I think this is how I would kind of set up. Maybe anytime, if they have this condition anytime before, yeah, is this a lifelong condition, or is this something that someone has like?
A lot of the times these patients already have the condition.
Okay.
I believe it is a chronic condition.
It's genetic. You're born with it.
Okay. Okay, so let's try this for our cohort. So we did find, with our really simple definition, we did find 2,000 people. We will save that. And there's no real inclusion report there because we didn't have any criteria, but now we'll regenerate it using our new updated definition. Now, what we're going to need to do is, what we want to predict is some sort of outcome, right? And we also have these 3 different nutritional interventions, which we could kind of treat as like subgroups of this. So while that's going, well, I think most important is actually the outcome. So the outcome would be, Rosetta, what did you say? The outcome is like a future stay in the hospital?
Right. Could be length of stay. Could that be an outcome?
Well, when we're doing research using these tools, the outcome has to be binary. So we have to make every outcome has to be like a yes or no type thing.
Can we do length of stay longer than, let's say, 5 days for now?
Okay. So the way we're going to code this is we'll just make a copy of this cohort and so these are going to capture the people who are in the cohort. And so they're going to enter when they have a inpatient visit. I wonder if we have length of stay in here, visit length criteria. Yeah, greater than 5 days. And we'll delete all these other inclusion criteria. Do we care about why they're in the hospital?
Just for the GI, I think it matters, but other than that.
Okay. So we'll say they need some kind of GI gastrointestinal issue. And we'll say maybe and here we're going to take all events. And since for outcomes, we generally want to capture every single outcome. We want to use fixed duration relative to the event. So they're going to leave the cohort, say 7 days, or we could say 5 days after they enter it. So if a person has this outcome multiple times, they're going to be captured multiple times in this cohort definition. Say GI. Okay. We will generate this one. Let's go back to our other one. Okay, so we're getting smaller numbers here, which might be a problem that we might not actually find anybody in our cohort. We can see that
You can switch to attrition view and maybe yes, it would be great. Yes.
So here's the attrition for our inclusion criteria. Age didn't affect it too much. We lost a lot of people with the GI diagnosis as we would expect, and then also the actual disease. But we do have 787 patients to work with. I'm just going to real quickly do a little test to see what the intersection is between our target cohort and our outcome cohort. So and so for this, we're going to have a time at risk. So this is a binary outcome. They're in the hospital longer than 5 days. And we need to think about what's the time frame that we're going to look to see if this happens or not. I guess I will take 3 years as just a example. And we'll say, okay, incidence of extended hospitalization. All right, so save that.
If you want, we can allocate a start date 30 days after, because our target cohort have inpatients, and so the hospitalization will last maybe a week, 2 weeks, and so if you want to, I don't know, because the 0 is they start,
Oh.
yes.
Like that?
Yeah, I think it would be.
Okay.
It should be,
But
I don't-
does it matter if the patients are only there for GI, their inpatient stay would be short? Is that okay? Because their inpatient stay might be like 5 days and not even.
7 days, if yeah, or
Yeah.
yeah.
7, okay, I'll do that. Generation. I see what you mean, Bazad. You don't want to capture the initial hospitalization. Okay, generation, save changes, rerun. Okay, so this is going to show us the intersection. If the intersection is 0, then we really can't fit a prediction model. Our numbers are going to be pretty small as it is, because this is a fairly rare condition. But yeah, here's our cohort for this. Does anyone have questions on sort of the process of cohort building? We're covering quite a lot quickly, and so if you feel like there's a lot here that you still have questions about, it's totally normal and fine. And that's why we have a bi-weekly Atlas office hours that you can all come to. It's an hour every 2 weeks. Anybody can show up and ask questions. We also have a Slack channel, which you can ask questions anytime on. Let's see if this finished. Nope, still going. Wanted to see if our outcome cohort had any, what that looked like. Okay, 41,000 people. I might try another cohort and just say greater than 1 day.
You can use the number of the days offset 0 the same. We can only consider a visit occurrence at the same day if we had increase the intersection actually.
Oh, to increase the intersection, we could only consider a visit that is 1 day.
Yeah.
Sorry, I didn't quite understand.
Because in the when we want to find the intersection, only the start date of the event and the cohort start date and can create our intersection actually. I want to say, because the end date is not so important, I think.
Yeah. Mm-hmm.
Yeah.
Yeah, so if we just say GI hospitalization, this will give us a more general.
Yes, more general, and so we will find.
And then close this. Okay, so with our more specific 5-day outcome cohort, we have 39 people who in that outcome cohort. So what we'll do is work on fitting a prediction model to see if we can predict what what happened with these, like how to predict which of these 705 people are going to end up having our outcome. One more thing I want to show you before I handed off is just how to look at these patients' records. So we have this idea that they're going to receive some certain treatment. What you can do is go to samples, and we'll take a sample here of say 10 patients, and we'll just randomly sample 10 people from this cohort, and we can look at their medical records essentially in Atlas. All right, so we have 10 people, age at index, gender, and if we click on those IDs, we get, we'll be taken to the profiles page. So this is their whole medical history, index around the index date. So 0 is the date that they were diagnosed with the genetic disease, and then we can filter and look at what kinds of treatments or things they had after it. So if we say, if we highlight a particular region of the graph, then we'll kind of be subsetting. We might say, not sure where we would find the so here's the Ehlers-Danlos syndrome diagnosis. So this is actually happening on day 13. So they had it on day 0 and day 13. But I might use this tool to kind of figure out what kinds of treatments people are getting if I'm looking for dietary treatments. I might search for nutrition, but there's nothing there. So that's just a tool we can use to kind of examine individual people and their records to kind of make sure we're capturing everybody and understand how their data is being represented. Here you can see like there are duplicates in the records. Like this is essentially the same observation, although it may be different. The source data may be different.
Can I ask you another question? So if I was interested in, let's say, multiple subsets of patients with, let's say, different diagnoses, like some patients have the ED syndrome and then others have, like, let's say, anxiety, and they were all kind of admitted for the same GI disease, but like would it be like within the, so like the index day would be the admission for GI disease, and then I would subset for, like, I would do either or logic to do either like the ED syndrome or anxiety, right? And then like that's how I would create my cohort if I was interested in like looking at multiple patient subsets.
Yeah, there's a couple ways that you could do it. One is to essentially copy your cohort definition, and then just like swap out the logic.
Mhm.
If you wanted to swap out the ED syndrome for anxiety, you could just copy it, and then import a different one here. Another way to do this, if you are looking at strata of this cohort. So if you want to stratify this cohort, like for example, when we looked at the incidence rates, we can create stratification criteria here. So here we could say add an additional condition. Let's say anxiety disorder. So now we're going to stratify our results by people with and without anxiety disorder. Oops. Import. Okay, let's try this again. Addition, import. Okay, I'll close this and not save any changes. Try again. Okay, so we're going to import the ID concept set.
While we're waiting, Pratyusha, did you manage to get the concept set to work? Great, thanks.
Oh, that's a little strange. Okay, I'm going to close that, go to concept sets. See if I can open this concept set. Okay, so this is a problem sometimes that happens, and there are concept IDs in this concept set that are not in the data. And the way you can kind of fix this is by making sure that you're pointing to the right data set, the right vocabulary version. But I think I'm just going to make a new concept set for anxiety medications or something like that. So let's see. Let's look at, there's nothing in ATC. Okay, we'll just do, here's a SNOMED code for anxiety. We'll take that and create a new concept set. Import, include descendants, save, close, and back to instance rates and stratification criteria, condition, import, anxiety. Okay, that worked. All right, and then if we save and generate, now we will have stratified results based on the presence or absence of the anxiety code. So that's kind of two ways to approach it. You can create two separate cohort definitions, or you can use the stratification.
That's really helpful. Thank you.
We didn't go through characterization or pathways. These are two very powerful functions in Atlas. But I want to make sure I give Behzad enough time. We kind of got a little bit behind on our schedule to go over prediction and stuff. But I think we have our we have a target cohort and an outcome cohort. So at least we have something that we can work with for the prediction study. So maybe with that, I'll hand it over to you, Behzad. That sounds okay.
Yes. Just see if the incidence rate is correct. So we have, because I think you changed the outcome cohort, and so let me know if we have any records in the incidence rate analysis. And so I can go first. I'm gonna go over the characterization. Let me share my screen and go through the characterization. Okay, thank you, Adam. So I'm gonna proceed with the characterization. So let's go to the characterization. And so let me characterize our created cohort and see how we can characterize our created cohorts and what kinds of characteristics can be considered here. So first, again, in order to create any characterization, you need to go to the characterization parts, and again, you can create a new characterization. In the characterization, we also have the feature analysis and the characterization. For each characterization, we need to define some features, and according to these features, you will be able to analyze and characterize your cohorts. In Odyssey, we have already defined features, and we can use all these predefined features. And also, you will be able to create your own features and characterize your cohort based on these features. Let's create our characterization. And so I will go over the feature definition. And so I will show you how we can. These are the advanced parts of the characterization. And so first, I'm going to go from the basic parts. So let's say training. Training characterization. Okay. So in the characterization, you will be able to compare more than one cohorts. For example, if you have 2 or 3 different cohorts, and if you want to compare all these cohorts with each other, you will be import all of these cohorts here and see what's the difference of these cohorts based on the features you have already defined, and see the statistics of these cohorts. Here we only have one cohort, and let's look at, I think, this was our target cohort, yeah?
I think so.
Yeah, okay. You can include any cohort that you have already created, and so here I only add the simple one, and so we have these cohorts, and we would like only to characterize these cohorts. And so in the feature analysis, I can this. Let me show you how many features we have. Okay, I go to feature types. In the feature types, as you can see, we have drug-based features, we have the condition-based features, 43, 15 measurements, and so visit, observation, device. Let's, for example, look at the drug. These are for me, these are all predefined features that have already been defined by the Odyssey. For example, the drug group era start medium term. And for each features, you need to define a period, for example. In medium term is referred to 6 months prior your index date. For example, you know, when you define your cohorts, we have an index date. Index date is actually your the start date of your the event that you have defined in the cohort. For example, in our cohort, you considered a visit, inpatient visit, and so the date of the inpatient visit is considered as an index date. And if you consider any features with respect to this index date, for example, we will consider the drug group era start medium term, and only the for example, for each drug era, only the start of this era will be considered, and all drugs era, for example, started between 6 months prior to the index date, or for example, inpatient visit, and will be considered in our characterization. These are the drug, for example, drug group era short term refer to 30 days. If you work with the Odyssey R packages, you will be able to change, for example, the short term. For example, you can, instead of the 30 days, you can consider the 2 weeks or 15 days, for example. Or but the standard values for the short term is 30, and for the long term is a year, and for the medium term is actually 6 months, 180 days. So all you will see the similar features with respect to each domain. For example, you can see the drug era overlapping, and you can see the description of all these features. Here you can see other kinds of the feature. For example, distinct ingredient count, medium term, distinct ingredient count, long term. It means any distinct ingredient used in a year prior to your index date. So is that clear? The features that we have here. And so let me look at the condition features. For example, the condition features here, you can see the condition group era again, the occurrence primary inpatient short term. And so you can go over all these features, and based on your characterization types, you can select one of these features, or you can define your own features. For example, here you can see some specific features, for example, the obesity prevalence, depression prevalence, and so all of these have been already defined. Okay.
Sorry. So
Yeah.
for each of those domains, so medium versus long term versus short term would be probably like different time points, right? So for a condition, it may not be also 30, or would it also be 30 days for short term condition era, versus short term drug era? Would everything be 30 days?
For the short term, yes, everything should be considered 30 days.
Okay, thank you.
These are the fixed. For example, if you see, for example, here, for example, the condition era, any time prior, we don't have any conditions regarding the time, and any condition era, any time prior to the index date will be considered. However, if you see, for example, the condition era medium term, all conditions 6 months prior to the index date will be considered. And for a long term, a year. Okay, so we are get back to our definition. Yes, we have our cohort definition here, and so I want to import some analysis, feature analysis. Okay, get to import. So from the we also have the demographic features. Okay, demographic. If you want, in most of the studies, we would like to see characterize our cohort based on the gender and based on the age groups, for example, and so demographic race. And if you want, you can add the age also and the ethnicity. These are the most important that you can see in most of the studies. So we can go also to condition. We have also charts on index. You can also use this kind of index features. So I also show some, for example, condition occurrence in long term. And when we consider the condition occurrence long term, it is we will have one covariate per condition in the condition occurrence table. It means that all condition, all the concepts that we have in a condition occurrence table, all the individual concept will be considered as a feature, as a covariate in our analysis. So we say, for example, long-term condition, and so let me consider a drug. And if the condition era is more, okay, and so the drug era, we can consider the drug group era long term. Okay, and so condition group. Condition occurrence long term. We have condition group also. These are a group of condition have been considered. So I think we can import all of them. So here you can see all the features that we want to consider in our characterization. Again, like you can also add some subgroup analysis. In the subgroup analysis, if you have, it means, for example, here we have 1, 2, 3, 4, 5, 6, 7 features. And so all the cohorts will be analyzed, will be characterized based on these features. Okay. So if you want to see with respect to each feature, we also want to see, for example, in the gender, we have maybe 100 patients female and 100 patients male, and we would like to see how many of these patients have an anxiety, for example. And so adding any subgroup analysis, divide individual statistics value, and we should be see, for example, for each for male, for example, how many of male patients, for example, has an anxiety, and how many of female patients have an anxiety, for example. If you add some subgroup with respect to the anxiety, if you want, we can also add the anxiety. So okay, so for the anxiety condition occurrence, and so we can add anxiety here. In the anxiety, we can consider, you can also determine any time period with respect to your index date. We may consider a year before and the 0 days. Each patient have any anxiety before, for example, before the inpatient visit. So this is the characterization design, and so we can save this. Do you have any question with respect to this definition?
No, makes sense.
Okay, so let's go to execute this. You will be able we can execute this and see what happens with the characterization. If you want to define your own features, I just show, for example, you can go to the new analysis, and so you can add the new feature analysis. Two kinds of, for example, you can determine your features is for example, which domain, and condition era, demographics, or measurement, observation, or procedure. So we have an anxiety subgroups, or maybe you can, instead of adding a subgroups, you can also consider features with respect to anxiety. For example, I can define a condition era. Do we have any? So here you will be able to, warning, you won't be able to change the type of analysis after save. Yeah. What? Okay. This is the criteria, and we have two options here. For example, for advanced users, they can define these features based on the native query. And so you can, this is a sample native query that you need some additional feature. For example, you should determine the covariate ID, for example. So this is a template that you need to use when create the query, the custom query. And so this is the criteria, more simple. In the criteria-based features, you have two options: prevalence or distributions. In the distribution, it looks like age. When we consider the age features, we need to see the distribution of age between, for example, two cohorts. In the distribution, you will have, for example, the mean, the maximum, minimum, the percentile info. But in the prevalence, you only have the number of patients with respect to these features. For example, we define, sorry, for example, you can define again the anxiety, add condition, era, for example, with anxiety. So at the same time, we had the subgroups. In the subgroups, the difference between the subgroup and features is that for each features in the subgroup, for each features, we will see the distribution of anxiety through our cohorts. However, when we define features based on the anxiety, this is a features, and you will be able, if you have multiple cohorts, you will be see the number of patients with anxiety in different cohorts, for example, only. So here you can also define time period, for example, a year before and 0 days before. And so anxiety, for example, before inpatient visit. And this is long-term. The long-term, it means it's 1 year before, for example, anxiety before. Long-term anxiety before inpatient visit.
But the way we defined it now, it would include all patients that had anxiety 1 year or less, or would it include patients who only had 1 year long anxiety?
No, it means it depends on your index state. And so in your cohort, for example, our index state is inpatient visit. And so we considered our observation period for this feature is 1 year before the inpatient visit. And so if you want to count how many anxiety conditions we have with respect to, and all of this is considered the binary features. And so if a patient have, for example, at least one anxiety condition, according to our concepts, so we will count that patients once. So for all, we will see how many patients have at least one anxiety 1 year before the inpatient visit. And this is the thing these covariates provide us. Okay. So
I just want to be mindful of the time, so we should figure out what we would complete, and then we can come back as it's past noon. So
yeah, this is finished, and so yeah. Okay, this is, for example, we have defined manual features, and so you can add, for example, in the characterization, this is finished, and we can see the results. And so in the definition, for example, you can also add, for example, this anxiety. Yes, long-term anxiety is here, and you can also add this in your own definition. Okay. So yeah, if you want, after lunch, we can go through the results, or if you want, I can show the results here. I don't know, Priya, after lunch?
yeah, let's do it after lunch, I think. Does that work for everybody? So we'll probably go on for about an hour after lunch, so we'll meet here at 1 o'clock. Can I get a show of hands that that works? Perfect. Okay, so we'll see most of you back here at 1, same Zoom link. All right, we'll see you then. Thanks, Bezad. Thanks,
Okay,
Sam.
thank you. Bye-bye.
See you in a bit. I'm just going to keep this on. So
Yeah, I'll just mute and stop video.
yeah, I'm just going to
Hi again.
Hey, Bezad.
Hey.
Hey, Adam.
Hi, Hannah. Hi, Bazad.
Hi, Adam.
Just emailed everyone that was in before the new link. Thanks, Randy. That was a really good shout. But I can't get back on the old meeting link. So hopefully everyone shows up. And if not, we can figure it out.
Who should not have access? Oh, I see what you're saying. Got it. I'll go to your link and do that.
Cool, thank you. Yeah, it wouldn't let me register because I'm a host, but it let me in the first time, which is a little odd. So I don't know.
Okay. Let me do that. So who are the other people? There was
Emailed
yes, there was Rosetta and
I emailed Rosetta, Pratyusha is here, so you made it back. Who else did I email? Oh, and Mia. I think that was everyone on the original meeting, unless I'm missing someone.
so Rosetta and Mia.
Rosetta, Mia, Hang Pham, and Pratyusha.
Oh, I thought I saw Pratyusha is here.
Yeah, yep. Perfect.
Okay. I'm gonna just email it to them. So just Mia and Rosetta, right?
Oh, I see Rosetta's on here now as well.
Oh yeah. Okay. I just emailed it to them, so hopefully that should be fine. But I'll just go stay in the other one just in case. I think we can go ahead and get started. if Hang and Mia join later, then they will. But let's go ahead and get started.
Okay. If you want, we can go over the result of the characterization. Yeah. Let me share my screen. Okay, can you see my screen?
Yep.
Okay, here, yes, our characterization. So in the previous session, we have created our characterization. And so again, we are looking at our design. We have used a couple of features, the demographic features and one condition occurrence and drug group error long-term. So I also noticed for the long-term anxiety, we don't have any patients. And if you look at the incidence rate for the anxiety, again, we don't have any case in our target cohorts. And so as a result, we will not have any, we couldn't get any results for this long-term. Instead of this, I added the depression prevalence features to see the depression prevalence 1 year before the index date. And so I also added actually define another subgroup analysis to show the difference between the features and the subgroup analysis. And so let's look at the same as the anxieties, only instead of the anxiety, we only consider the depressive disorder patients and 1 year before the inpatient visit. Okay, so if you go to execute and I show you the last run. Okay, so this is the page that you can explore your own the whole result of the characterization. In this part, you can see if you have multiple cohorts, you can select, for example, if you want to compare only 2 cohorts, you can, for example, you can select only two of them. So if you want to see all together, you can select all of them. And at the in the analysis, we have all, for example, all the analysis have been checked, and so you can see the old result for the drug group error, condition occurrence, demographics, age group, and etc. And we also have, as a result of these features, we have selected 4 main domains, for example, the drug domain, condition error domain, demographics, and condition. And so you can select any of them. So we don't need to. And here, the first table is the old prevalence covariates and stratified by the long-term depression. And this is actually our subgroup analysis. As you can see, for each individual covariates, we have the count number and the percentage. For example, out of how many patients we have, for example, we have 700 patients. And so in our target cohorts, and out of 700 cohort, for example, we have 680 patients with this covariates, for example, nervous system. And this is actually 86% of the whole target. At the same time, you can see the distribution of the patients with respect to this covariates with respect to the depressive disorder. For example, out of 6, for example, we only have 207 patients with depressive disorder, so having the nervous system. And so, but we don't know the total number of, actually the 95% of the whole depressive disorder patients is shown here. If you want to know how many patients we have depression, I have included the features with respect to depression. Let me see, where is it? long-term anxiety. As you can see, the 0, and here is the depression prevalence. And I consider the depression prevalence as a features and I also used it for stratification. As you can see, we only have 217 patients, and if you consider depression disorder as a features, this only show, for example, the count number, the percentage of the whole cohort. For example, 27% of the patients in our target cohort are depressive disorder, has depressive disorder condition. And so again, as we have a stratification, as you can see, the number is the same. And so you can see in all, for example, in the all other covariates, we have again the distribution of this depressive disorder patients over the all covariates. For example, we have the female, and among the female, for example, the female constitute 90% of our target cohorts, and most of the patients are female. And so we also, as you can see, we see 201 of the patients are has depressive disorder condition. So if you can go from the drug group era, and so again you can see the drug era groups in the separately, and so you can see the number of patients and the number of patients with respect to our stratification. You can add multiple analysis. For example, if you want to see the distribution over the diabetes. However, in the subgroup analysis, this applies for all of the covariates. And so you can see the distribution of this the subgroup analysis over the all covariates. Again, you can see the condition occurrence long term. And so if you want, you also can explore all of these patients. For example, by clicking the explore, you can see the details of, for example, here you can see the ancestors and the distance. This is actually the ancestor level. And so the concept name and the old straw. And so all the detailed information can be achievable by exploring each covariates. And you can see, you know, most of these covariates are general covariates, and so maybe they have descendant. And so you can see the distribution of the other concept with respect to these covariates in the explore part.
Sorry, could you just explain what the distance is again? I missed that.
The distance?
Yeah.
Let me see. If you remember in the Adam showed the hierarchy that we have through the Athena, and so for each concept we can determine the distance. For example, in order to see what's the position of this concept in this hierarchy. Okay, so you can say I only considers two by taking difference between the level of the concept. You can determine, for example, if you want to see go up, for example, 2 level and see the concepts 2 level up the current concept, for example, or you want to see the descendant, for example, concepts. And this distance is determination. For example, this is the clinical finding, and this is the distance in the 4. And I think it will be difference. Adam, do you know this is a difference or exactly the value of the for example, this the 4th level of the clinical findings, the 4th level with respect to this which covariate is selected with respect to that. Do you know, Adam?
I think it's the fourth level up from the current concept. So like your current concept is the the Ehlers-Danlos syndrome. So if you go up 4 levels in the hierarchy, that's just telling you that that top. So scroll back up to that top one. The clinical finding. That's 4 levels away from the one that you're at. So that's a really general concept, clinical finding. And it's, yeah, so you have to make 4 steps essentially to get from the Ehlers-Danlos syndrome up to clinical finding.
Yeah, actually, this is a difference because, for example, here you can see the 0, and so we have the descendant as a -1, and this is the first descendant, and so this is the second ancestor, and this is the 4th ancestor, and so yeah.
Okay, so can I just double check? I think I understand this in general. So is what this chart showing us right here is with people in our Ehlers-Danlos syndrome cohort, these are conditions or concepts that are also found within that cohort ordered by, or so say like order of soft tissue, which is 3 above it, there's 2% of the
Let me, I got it. So actually, when you consider this covariates, these are individual concept IDs. And so when we want looking for the occurrence of this, for example, the chronic pain. So this chronic pain has a concept ID, and when we are going to figure out for example, the patient number with respect to this concept ID, we only consider the chronic pain concept ID. Maybe in our records, some patients, the descendant concept ID have been used, for example, in some patient records, or maybe it depends on how the information have been recorded. And so when we go to the detail of the for example, chronic pain, we will be able to see the distribution with respect to general concept IDs or for the descendant concept IDs. However, this distribution is related to exactly the chronic pain concept ID. Okay, so according to maybe for some patients, instead of chronic pain, someone enter the descendant IDs, and so we didn't consider those patients in this distribution. Okay, so as a result, you can go to the Explorer, and so for example, as you can see for the ancestor, we only have 4. What does it mean? Very few patients only recurred by this clinical file, by this ancestor, by this concept ID, and because these are very general, and so when we record all the patients, we need to add appropriate concept ID that show the details regarding the diagnosis or regarding the drugs. And so, however, for example, the chronic pain with a 0 that's selected has the most the greatest number, and so the high number is related to the chronic pain, and the others is very low.
Oh, I see. So when you click into each of these different conditions,
yes. For example, if you go to this client ancestor, you can also again explore.
And then this is, sorry, this is my last question on this. So when you click into each of these distributions, you get the distribution for each one. Is that over the whole data set or just over our
cohorts?
Over the cohort. Okay.
Yes,
cool.
yes. If you consider all this distance is calculated based off this general, as we selected the general, the clinical findings, the most general concept, and as you can see, all the other concept is a descendant concept with respect to this, and so we have the -1, -1, -2. Can you see?
Yeah. Okay. I think I understand it now.
Bazad, why is the clinical finding have only a couple people that have that? 'Cause it seems like everyone would
have. The clinical finding is a general concept, and so it doesn't show anything.
So this is just this is only 4 people have have a clinical finding code, and not many people would actually have a clinical finding code because it doesn't really say anything, right?
I think, yeah, it is. It can be considered as an error, and so noise actually, because we, if you allocate clinical findings for patients, it is not informative. And so if, for example, here is a condition occurrence, and so instead of, for example, determining any specific diagnosis or condition, we only say this patient has a clinical finding, for example. Okay, so okay, and so for example, here you can see the ethnicity. And so please consider when we say the prevalence greater than 1%, it means that all this distribution have been calculated. We only selected all the covariates having more than 1% prevalence. And so you can change this. And so all of this distribution will be changed. For example, you can say 10%. So more frequent features will be considered. Here, we filter the results to covariates with prevalence greater than 10%. And so we selected, when we want to calculate the distribution, we only considered all the covariates having at least 10% incidence prevalence, actually. Okay. So again, this is the characterization based on the age groups. For example, we have let me get this 1%, so we will be able to show, I think, all the age groups. Yeah. In age groups, you can see, for example, in some cases, the prevalence rate was low, and so by increasing the prevalence rate, they excluded. And so you can see, for example, from 1519, we as we considered the patients greater than 18. So this number, I think, the 26 is related to patients with 18 and 19 actually. And so for the other age groups, you can see the distribution of these cohorts over the different kinds of age groups. The same information is available for the race, the white, Asian, and Black and African Americans. And so the female and male, you can see the distribution between the female and male. And here you can see the demographic age. As already mentioned in feature definition, if you define the distribution features, for example, here in the anxiety, for example, we had the distribution-based feature or the prevalence-based features. And so if you select the distribution, you looks like the demographic age. For example, you will have the person numbers, the age, standard deviation, minimum, maximum, median, and all of the distribution of these features will be determined for all the cohorts. For example, we have only one cohort, and so all this row is related to the whole cohort. And we have also depressive disorder subgroup analysis, and also you can see the distribution, the age distribution with respect to this subgroup, our subgroup cohort. And so this is the depression prevalence, and these features is actually like the anxiety, and so we have considered the prevalence. So you can see for the anxiety and for the depression is the same, and so in terms of the prevalence. And however, the age is distribution features, and so you will be able to see for example, the average, minimum, maximum percentile, and all other kinds of information. Do you have any questions so far? Okay. this is the whole, I don't know, Adam, if I miss something, you can add, I don't know. I try to show the specific parts of the characterization. And so just, we only use one cohort. However, you can add multiple, more than one cohorts and compare the distribution of these features among two cohorts. And this is the specific purpose of the cohort characterization, to compare multiple cohorts based on the features that you have defined.
Yeah.
Yeah. Okay.
Great.
So if you want, the next part is the prediction, and so it is so easy to make a prediction package by using the atlas. So if you want, we can go to prediction package, and so I'm going to create a new patient level prediction. Okay, this is training prediction. Okay, so for the prediction, the first part is to determine our target cohorts. And so as we already define our target cohorts, I'm going to use this was yes, Adam. So
Let me see.
Wasn't it the
Yes.
Yeah.
Oh,
yes,
that's
yes.
that's the target one. Mhm.
The target cohorts. And so we will add, this is our target cohort. The outcomes, again, we will have another cohorts that determine our outcome patients. And so which one is correct? This one or this one? I think in hospitalization longer than 5 days.
Both of them.
Yes, I can use
Yeah.
both. Okay, you can have multiple target cohorts and multiple outcomes. In this case, so all combination will be considered, and so you can see the model, for example, with respect to these outcomes and with the same target cohorts or with the other outcomes. So it is possible to add more than one target cohort and more than one outcome cohorts.
Can I
And
ask a quick question regarding that? So now we have the GI hospitalization, that's the whole cohort of patients that stayed for over 5 days or less than 5 days, like that's the whole thing, right? Versus when we have the cohort that had longer than 5 days stay. So in this case, wouldn't we be interested in looking at patients that had shorter than five days stay versus longer than 5 days and not the whole thing? Does that make
yeah, this depends on your definition, and so based on you can define the outcome based on your own desired requirements. And so I mean, this is optional and all depends on your criteria. So if you want to, for example, in this case, we are going to predict all GI hospitalization longer than 5 days from the start date. Our everything will be calculated based on the index date that we have defined in the target cohorts. For example, here in the target cohort, we have actually the index date is the visits hospitalization. So the visit occurrence date, and so according to this, we will define the outcome cohorts, all events, all GI hospitalization.
Yeah, I guess like my question was, since we're interested in comparing patients who stayed longer than 5 days to patients who stayed shorter than 5 days, would we define in reality, would we define the cohorts differently, right? This is just
yes, exactly. You should define, for example, 2 outcome cohorts, and so or we can add here and see, for example, the impact of the predictive models for both outcomes. And if you want, for example, change predict based on different kinds of target cohort, you can for example have some maybe you can extract some other cohorts from your target cohorts with specific characteristics, and so you can see how the model trained based on this target cohort or based on these outcomes. So the important things when we want to calculate the positive case and negative case, the intersection between the target cohort and the outcome cohort is considered. In both cohorts, we have index states. For example, if we go to the definition of the cohorts, yeah, this is yes, this was the target cohorts. Okay, and this is our outcome cohorts. Okay, as you can see here, our event is the visit occurrence again. Okay, visit occurrence with visit length greater than 5. Okay, this is independent cohort, and so it is not independent from our target cohort, I mean. And in our target cohort, you may your initial event may be completely different, and it can be considered a procedure or diagnosis or anything else. So in our target cohort, a visit occurrence in patient visit is our target cohorts, and all inclusion criteria are defined based on this, and all the inclusion criteria are defined based on this. Okay, the intersection of these two cohorts will be considered our positive cases in our prediction problem. In order to define this intersection, we need to define some other things, and so I will mention in the, for example, in the population settings. And so just only you need to know all these cohorts are independent, and so and both have their own initial events with index state, and the outcome again has its own initial event with own index state. Okay, so let's go to analysis settings, and I will explain how we can find the positive cases based on our population setting. In the analysis settings, we need to add our models. For example, here you can see we can add loss logistic regression, random forest, and other more other machine learning algorithms. So for example, if we add you can add the loss logistic regression, so you can determine the default value for this parameter. Loss logistic regression only has one parameter, and so you can consider the default value. And again, so we also add the random forest, for example. And here you can see we only have 3 parameters, the 4 parameters with random forest. And for each parameters, you can select more than one default values. For example, the max depths, we have 4, 10, and 17. And this is because we don't know which of these are the best. And so you can consider 3 parameter values, and through the cross-validation, this package, the prediction package, will find the best hyperparameters based on the all the values you have entered here. For example, you can remove, for example, here we can consider only 10, or you can also add, for example, 15 and add here. And so we can consider the max depth between, we can examine between this 10 and 50. For example, the number of tree features, the default value is 10 because the number of features can be selected automatically by the algorithms. And here, so we have the number of trees to build, and so the default value is 500. Maybe you can test with the low number, for example, 100. And this is the perform an initial variable selection prior to fitting the model to select the useful variable. You can the default value is true, and it is we keep this value as a default value. So this is for each algorithm, you will have different hyperparameters, and so you can add your desired values for each parameter and test which value achieve the best prediction for your case, for example. Just as I want to, please consider if you add more values, the training process will take much time, and so because for any combination, the training will be down. And so if you add more values for each parameters, so the training time will be huge. And so if, for example, if you have multiple algorithms with multiple parameter values, so all the combination will be considered. Here, for example, we have 2 outcomes, and all the parameter will be tuned based on each case. For example, if you have for each target cohort with each outcome cohort, each algorithms, and each of these parameters. Okay, just I want to have a low training time. So if you we can remove this, and we can remove this, and I try to have 1 parameter because I don't want to. I want to show you the results, and so yeah, we define two algorithms, and so the next step is defining the covariate setting. Again, looks like the features that we had in the characterization, we have the same in the covariate setting, and so you will be able to add your own desired covariates. For example, here is the default values that we have. So this part is related to the demographic features. For example, we can add the gender or age groups, race, ethnicity, and don't want, for example, the index months. And also as a demographic feature, we can select this. This is time bound covariates. For example, you can, as you remember, we talked about any time prior for the long term, medium term, and short term, and the end days. You can change the default values. For example, you can consider the medium term as 3 months or 6 months, or for the long term, you can consider the 3 year, for example. And these are can be changed from here. And so for the, here is set the bound era-based covariates, for example. Again, for the era-based covariates, we have only the condition and drug. Only for condition and drug, we have era tables. So, for example, you can consider the condition group or condition itself. When you consider the condition group, we consider the ancestors, actually, the most ancestor concepts, but with all descendants. We can consider the condition group and drug group for here, and long term. So if you want, as I want to have a short training time, I don't want to select more features. So for the other covariates, set the time bound covariates, for example, we have for each domain, we have, you can define a covariate. For example, if you want to consider the condition in the long terms, and the procedure long term, I don't want to consider the measurements. We can consider the procedure, the drugs, for example, in long term, and you can also consider the same one for the short term. For the condition and for the drug, you can also consider the short term and the long term. Okay, you can also select the index, and so I don't want to select because I want to, it will take much time to calculate, and so this is the default values, and also you will be able to determine specific concept IDs to be included in your covariate. For example, if you want, you can add a list of concept IDs that you want to include it. And so when we calculate, for example, the procedure, the measurement, or conditions, only covariates that match your included concept IDs will be will be added to your covariate settings. Okay. At the same time, you can define, for example, all the concept IDs if you want to exclude, and so we can also determine these concept IDs here. And so when we calculate our covariate tables, your covariate tables can be created based on your included concept IDs or excluded concept IDs. After that, so after defining our covariate settings, yes, the most important part is the population settings that directly affect the intersection between the target cohort and the outcome cohort. So let's go to the population setting. This is very important. The first one is define a time matrix window. So what is the time matrix window? And so, for example, if you want to see the intersection between the target cohort and the outcome cohorts, we need to know which time will be used for matching. So, for example, here the default is the 1 year. You can consider start date and end date, and the target cohorts actually. So we consider the start date of the 1 day from the start dates. And so if you want to consider any hospitalization during 1 year after the start date in the target cohort, you can consider to 365 days from, again, the start date. So we considered actually any hospitalization in this period. So if any patients have inpatient visits during this between these two time point, for example, 1 day after the start date and 365 after the start dates, any hospitalization occurred in this period will be considered as our positive cases. Another setting is that the maximum look-back period applied to the target cohorts. And this look-backs is our observation window. When we want to calculate, for example, calculate the covariate values, this is our observation period. Let me show you maybe the patient level prediction. Yeah, this picture is show the observation period. For example, this is the start index date, and these are our time matrices, and the outcome can be occurred, for example, at this point. So when we want to calculate our covariates, we can consider this window, this observation window, and this we determine which observation period will be considered when creating our covariate values. Okay, so we can consider, for example, 1 year maximum. The maximum period is this, and please consider, for example, when we define the covariates, for example, we have a long-term, short-term. When you selected the short-term, only 6 months will be considered, and the observation period for those features will be 6 months, and this is the maximum. For example, for the long term, we have considered a year, and this value only select the maximum look-back period applied to the target cohort. We will keep it as a default value, and should subject without time matrix be removed. When we talk about the time matrix period, according to your target cohort start and end date, we have 2 time period start, and for example, here we have a 1 year time at risk. At the same time, maybe your target cohort, the end date of your target cohort is 3 years, for example. So when we consider the positive cases, we look at all the patients having with a complete time matrix period. Maybe some patients, the end date for some patient maybe is less than a year, So these patients doesn't have a required time matrix period. So this question is that if we have a minimum time matrix 364, if you want to keep all patients with having the whole time matrix period, or if they don't have, for example, if they have a short time matrix period, they will be removed if you set this as a no. Okay, for our case, I don't know, it's more meaningful to keep or what do you think?
I don't really know.
The time matrix is required for determining our positive cases. For example, if patients, in this case, if we set as yes, if a patient have, for example, the end date is not a full year, so we will exclude all of them, because we say we need to patient having the full time at risk and see if they have a full time, for example, 2 years, the patients.
I guess in this case, I don't know if it matters, because if it's for the ED syndrome, since it's a genetic disorder, they will have it for the rest of their life, for their entire life. So I guess it maybe doesn't matter.
Yeah, so for this case by case, this can be different. And so according to your case, you can determine, do you want to keep these patients or you want to exclude these patients? Others is that the first exposure per subject. And this criteria should only the first exposure per subject to be included. For example, in the cohort definition, you have considered this is our type course, for example, all events per person. And if you consider, for example, you can determine in this parameter here, or you can determine in the prediction. And so these settings actually can be determined in different places. And so if you say, for example, the first exposure per subject be included, so you can set this yes, or if you don't want, you can set no. Okay, remove patients who have observed the outcome prior to the cohort entry. So maybe in some cases you need to, if any outcome happened before the start date, these patients must be included, must be excluded. And so this is again depends on your case. And so if you want to remove patients who have observed the outcome prior to the cohort entry is the start date of the cohort. So if you have any hospitalization before the start date, you may want to exclude these patients. So in our the default value is
I don't think.
no.
Yeah, I don't think we need to do that.
Oh, okay. So according to these population settings, we will be able to determine the intersection between the outcomes and the target cohorts. Okay, and the last part is regarding the execution settings. For example, the perform sampling. If you want to have the sampling, you will be able to, for example, if you have many patients and you don't want to include all patients, you can determine a sampling strategy. For example, how many patients to use for a subset, and so you can determine the number of patients. So the other thing is maximum covariates, minimum covariate occurrence, and so this is related to the prevalence rate, as I showed you in the characterization. If you want to include all covariates having at least 0.001 prevalence rate. And so if you want to add more frequent features, you can increase this value. If you want to have frequent and less frequent features, you can keep it in, for example, this number. And if you have the normalization, if you want to normalize the covariates, you can, yes, the normalize, all the feature values are normalized based on the maximum value. So if you don't want to normalize the covariate values, you can set as no. So the training setting is determined two types we have for split the test and train. You can consider the time-based or the person-based. I think, yeah, the time-based and person-based. In the time-based, maybe if you want to see the generalizability of the models based on the time, the temporal generalization, for example, you can train the models between patients, using patients between the 2010 and 2020, and you can test your models in patients after, for example, 2021. So in this case, you will be able to evaluate the temporal generalizability of your model. And so in the person, we don't care the time, and so randomly we can select our train and test sets randomly based on all the patients, not the time. So the percentage of the data splits, for example, how many what percentage of the patients you want to be tested, and so you determine, for example, 25% of the patients will be considered as a test set, and 75% will be considered as a training. So in the folds, you can determine the cross-validation folds, and so if you consider the 3 folds, the whole training set will be divided to 3 parts, and so the 2 parts will be used as training, and the last part will be considered as a validation. So all the hyperparameters will be tuned based on this. So we consider the 3 folds, and you can also consider a seed as we have a split. And if you want to repeat the experiments with the same patients, you can consider, for example, here any number, and so with this number you will have you will always have the same split, and so you will be able to reproduce your results with the same split data. Okay. Any question?
Behzad, do you want me to show the results app?
Yes. So let me.
We need to wrap up.
We only have a few minutes left, I think.
Yes. I will save this. Okay. So if you want, you can run from this, and I'm running. It will take, I don't know how much does it take, and so if you want, I can show.
I ran the previous one.
Yeah. If you want, I have a previous one. Let me see. Yeah. For example, we have the same. For example, here you can see the more than algorithms and 1 target and 1 outcomes, and these have already been trained. And so after training, so you will be able to download the prediction package. For example, and I'm going to show the output of this package, and so I will try to download this. Okay. The zip file will be downloaded here, and so you can unzip and go to the results. As you consider it, if you go to the result folders, you will see the 6 analyses with respect to, for example, here we had 6 analyses, 1, 2, 3, 4, 5, 6. And so based on your analysis settings, you will have 6 analysis folder. And if you go to analysis 1, the analysis 4 in the random forest, for example, and if you open the prediction package, yes, I have already downloaded. Okay. For example, you can see the cohort ID and the outcome ID, the cohort size, and the covariate number. And also you can see the train set evaluation here, the performance, the AUC value with respect to in the train set, and the AUC value in the test set. this is for each analysis we have a log files, and so all for if you want to, for example, transfer these models to other clinical sites and tests, you only need to have these folders. And here, this is the model folders includes the index, but all these outputs is related to the old version of the PLP package, but the structure is different in the new version. However, we will have you only need to know we will have a model folder, and so if you transfer this model folder to any other clinical site, you will be able to run these models on the data that we have on that clinical site. Okay, so in the model, for example, you have the attribute, the cohort ID, and the hyperparameter search, the index, the model itself, the RDS files, and so I don't have time to go to the details of this, but the other things is here important, the Shiny app, and the Shiny app is automatically created by running this package. And so, for example, if you go to and run the server.r and click, and I will try to run it. Okay. Yeah. If you run this, the server.r, the Shiny app will be launched. And again, you can see we have 6 analyses. And so if you click on the first one, you can see the time at risk period. For example, here the time at risk period is 90 days, and the AUC value, AUPRC, and so the target size, the outcome size, the incidence rate. Okay, so if you select one of them, and so here you will be able to select if you have more than one development database or validation database, you can select from this. And so if you select one of them and go to the performance, you will be able to see the details of the performance. For example, the threshold of the prediction, different threshold can be considered. And for example, in this threshold 0.1, the incidence is 15. And so the sensitivity and the PPP value, if you change the threshold, for example, you will have different, you will see the different performance. For example, if for the low threshold, we will have a high sensitivity, but the PPU value will be reduced. Okay, so if we want to consider the sensitivity of, for example, in sensitivity 72, we will try to show this Shiny app will show the discrimination results. If you go to this discrimination, you will be able to see the ROC plot, the precision recall plot, for example, the F1 score again. And so based on this threshold, you can see we have selected this threshold. If you change the threshold, for example, here, the discrimination result will change, and you can see, yeah, if you increase the threshold, we will have the false positive rate is reduced, but we will have a true positive rate. And so you can see the position of the threshold, this threshold in the precision recall curve, the F1 score plot, and also you can see the prediction score distribution, and that shows how our model is discriminative, and so can discriminate the positive class from the negative class.
Yeah, very cool, Bezal. Very cool. I just want to be mindful of the time. It's already 3 minutes past 2. So maybe we can quickly, Adam, do you want to quickly show the, like, if you actually run this network study on multiple different databases, you can actually collect them together, and what that looks like?
Yeah.
Sure, yeah. Okay. What I was looking at actually is I think here, yeah, so here are the results for the prediction study that we just, or the prediction analysis we just came up with. So when on the break, I ran the analysis, so it took like less than an hour. And then we have our ED syndrome and hospitalization outcome and our AUCs. So that is there in Atlas.
Where is this? Oh, okay. So we can go into Atlas and look this up. Patient level prediction number 75. Rosetta, you may want to remember that. So this
Yeah.
will be forever stored in Atlas.
Yeah. Yep. So it took like 20 minutes to run, and I just did lasso religious regression, but I had a couple different. I had 2 different outcome cohorts and etc. But then, yeah, to your point, Priya, if you go to data.odyssey.org, here's the Women of Odyssey breast cancer study. You can run this on multiple databases, and you can validate a model trained in one database on a different database and kind of combine all this information into a single view. And
it's kind of really nice to contrast how your model does in different databases, because so like if you click on the development database, we can actually see on the left, right? So those are all the databases that are actually there.
STAR.
Yeah. So this is when we ran it.
Yeah, so if development and validation are the same, it just means it was trained and evaluated on the same database using a trained test split, but you can also develop on one database and validate on a different one. But yeah, so I think that's what we have for today. And thank you all for joining.
Yeah, thank you so much, Adam and Behzad. That was a lot of information. I think it was really cool. I think we all got an individual workshop, so that was pretty cool. Thank you. And thanks for providing examples, Rosetta. But Pratyush and Heng, thanks for joining. If you have any questions, feel free to join us at the Atlas office hours. They're every other week. I think you should have, they usually post them on the Slack channel a couple of days before. But with that, I think we should call this workshop done.
Yep. Thank you so much. Thank you, guys.
Thank you.
Welcome.
Thank you so much. Thank you so much, both of you.
The preceding program is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at med.stanford.edu.